Boy, it feels like Monday, doesn't it? It's weather. All right, well, it's 9 a.m., so let's get started. Hope you all had a good spring break. Yeah? Do you remember at all what we were doing? Related rates, word problems. I've given you these this worksheet to help us get through these problems. Yes? Everyone have a copy of this? You need one? Yeah? I don't have many, but I think I handed out, what, like 4 or 5 to each of you? Or 3 or 4, yeah? Just a couple more. All right, so we're going to pick up. I realize, spring break, yes, get it. But let's try and get back on track as quickly as possible here. So let's run through the idea, the major steps of these word problems. We want to read the problem. We want to think about something that's in motion, drawing a picture that represents that general situation where things are moving, then draw a picture of things like this snapshot in time, that within the problem there will be a question about asking how fast something is changing at an instant in time. So we need to draw that picture. We need to assign variables. We need to assign constants, things that do change in the problem, things that don't change in the problem. Then we want to write down what we're given and what we want. Then we find an equation. Then we do implicit differentiation. And then we plug everything in and solve the problem. Okay? That's the general idea. This is a classic problem. Like all Cal 1 students see this problem right here, the ladder problem. So we've got this 20-foot ladder. It slides down a wall, so it'd be something like this if we had a ladder. And we start something like that, right? Slides down the wall. So it says here that this 20-foot ladder slides down a wall such that the top of the ladder is moving downward at a constant rate. Rate means derivative. Okay, rate is a speed. Rate of 0.5 feet per second. At the moment the top of the ladder is 3 feet from the ground, how fast is the bottom of the ladder moving away from the wall? All right, so I'll animate this for us. There's our ladder, it's falling. Right? It's slowed down a little bit just so we can kind of see what's happening. The ladder's falling. And so what we're given in the problem, of course, is that it's a 20-foot ladder, right? That's not going to change. The ladder's going to stay 20 feet the whole time. We're also told how fast the tip of the ladder is moving down the wall. That's given to us. Let me zoom this out just a little bit. Yeah, okay, that'll work. So it says that the top of the ladder is moving down the wall or downward at a constant rate of 0.5 feet per second. So this is a constant speed. The rate at which that tip is coming down is 0.5 feet per second. And the question is, at the exact moment that this distance from here to here, at that exact moment that that's 3 feet, we want to know how fast that point is moving away from the wall. Do you all see that in the beginning, this point right here moves quickly? See how fast it moved in the beginning? Watch that point, it's going to come back. Here it is. See how fast it moved in the beginning, and then as this comes down, it actually looks like it slows down, doesn't it? So we want to know at some exact moment, let me actually snap to the exact moment in time. It's this moment right here. At that moment, when this is 3 feet, I want to know how fast that point's moving. Understand the question? Any questions on the question? All right, let me leave this up here. move this out of the way. And let's start to fill out this sheet, all right? By the way, we are a little bit behind in class right now. If we look at our schedule, we were supposed to have spring break. And before spring break, we were supposed to have already finished related rates and started 3.3. So we're still here. We're supposed to be starting 3.5 today. So we're I don't know how we got this far behind, but we are at least a week behind. So we're just going to try and make up as much time as we can. I'm not sure where, but we will. My goal is to prepare you for Cal 2, regardless if you're taking Cal 2. That's my job, is to prepare you for Cal 2. Yes? I don't have many of these left here, but you can have that one. I gave these out last time, right? Okay. So, and then these are also on Canvas. If you go into files, I have these. You can print them out at home. All right? All right, so here we go. First thing I'm going to do is I'm going to draw a picture. I'm going to draw my two pictures. One at the general situation. So here's my general picture. My general picture is that I have the ground and then I have a wall. Which side I put the wall on doesn't matter, but to match what I had in my animation, I'll make this the wall. It's supposed to be a straight wall. Okay, good enough. And then I have a ladder, right? And then my ladder is like this, right? Here, here. And this I can say is 20 feet. That's never changing in the problem, right? Now what we have to keep in mind here is in this general picture, right? This is moving down, that is moving out. So things are in motion in this picture. As opposed to the instant in time picture, at the instant in time picture, it looks like this. Oh, okay. Here, my ladder's like this. This is still 20, right? But this is 3, right? Because that's the moment in time that we're referring to in the question. Remember I told you last class when we first started this that you don't have to do this in any particular order. You just need to get all this information down. So let me see, what am I given? And what do I want? Right? So I'm given, what I'm usually looking for in these problems is some derivative, right? The derivative of something is being given. The derivative is a rate of change. I am given a rate of change of 0.5 feet per second. What is that though? That's the change in what? It's a speed, which is a change in distance over time, but I'm saying in terms of our picture, it's change in what? 0.5 feet per second. What's changing at 0.5 feet per second? The height of the ladder, not like this distance right here, right? Which we have not labeled, right? We have not assigned a variable to it. So this would be a good time for us to call this side of this distance from here to here. This would be a good opportunity for us to label that with a variable because it's changing, right? So what would you like to call the distance from here to here? And you can call it anything you want. I would avoid x. Usually we use x for left and right. Use y for up and down. You could use h for height of, whatever you want. So what do y'all want? What? D? Okay, D's the one the other one I don't like. Only because when you write D, 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 T, it just looks weird to me. Right? Like D, D, it just, I mean, if you want D, you can do D, but I will never use D in class, so, unless someone requests it, right? Let's use H. Okay? So we need that, right? We have to have that because this given rate of change, 0.5 feet per second, is the rate at which H is changing, right? That's how fast the H is changing. So I need to label that so I can write dH dt equals 0.5 feet per second. Do you understand? We have to have the variable H in order for this to be able to be written this way. Yes?
Is it negative 0.5 since it's going down?
Okay, so now we have to talk about, is H growing or shrinking, right? So is it growing or shrinking in this case? It's shrinking. And we did a problem, again, before spring break where it was a plane flying over. And we had talked about if you're talking about the plane coming towards you, then the distance was shrinking. If it's moving away from you, then it's growing, right? So because h is shrinking here, getting smaller, this rate of change would have to be a negative value. We'd have to look at that as a negative rate of change. So we have to include that right here. So what I always like to do is put what we have first, and then determine is it growing or shrinking, and that will determine if it's positive or negative. Okay, that's what we are given, right? What do we want? We want to know how fast the bottom of the ladder is moving away from the wall, right? Relative to the wall, how fast is that moving away? So I want to know this distance from here to here. I want to know how fast it's growing, right? So we haven't labeled it. So we should label this distance, right? Why don't we call it, what? B? I thought you said D. I thought you were just messing with. You want to call it B? We'll call it B. For bottom or something like that, or base or something. You can call it X. All right, so B. So we want to know what then? How fast B is changing with respect to time. So we want to know D, B, dt. That's what we would like to find. But not dB dt like at any random point. At a specific point in time we want to know, right? At what moment do we want to know this? At exactly what? At what's 3 feet? H. See, it says when the top of the ladder is 3 feet from here, right? But isn't this always H? So to say that we want to know how fast this point's moving away at exactly this moment is the same as saying what's dB dt at the moment that H is 3 feet. Okay? We're given the rate of change of H with respect to time. We want to know the rate of change of B with respect to time at exactly the moment that H is 3. All right. I think we've got everything set up here. The next thing we want to do is come up with an equation. And that equation must be in any equation you can think of. Looking at the geometry of the problem, you must look at this picture, not this one. Looking at this picture, is there any geometry that you see that would connect what variables together? What variables do I have to connect? B and it's always going to be this variable here and this variable here. You have to come up with something that's going to connect the H and the B together in an equation. Do you all see it? Look at this picture. Any equation you can think of that connects H and B together? Say again? So that's the area formula, right? There's an area formula for that. The problem with the area formula is this. If you use area is 1/2 base times height, then yes, B will be in this equation, H will be in this equation, but so is A, capital A, and we don't have any information about capital A. You have to think about what would happen if you differentiate this now. Okay? If you differentiate this, does everyone agree that you will get a dB dt somewhere in there, in the differentiation? You will get a dH dt somewhere in the differentiation. But you'll also get a dA dt, which we know nothing about, right? So even though that is a formula that connects B and H together, it's probably not the best one. There's probably something else that won't require us to know anything about area. Go ahead. Pythagorean, right? Don't we have a right triangle here? I mean, this is a right triangle. And so you could use Pythagorean, which says that you take, well, a squared plus b squared equals c squared, right? That's the Pythagorean. Let's use that. For us, it won't be a squared. It'll be what? You can say h squared plus b squared equals 20 squared, right? Now, we don't put c squared here because actually the hypotenuse is always 20, isn't it? Like it never changes. So we can actually assign that constant. In fact, you don't want a c there because you'll have the same problem you would have had here. What's dc dt if you took a derivative you don't know? Got it? All right, that is an equation. It connects h and b together, and I can now differentiate it implicitly. Before I do it, let's just square the 20. It's 400, right? Okay, that's my equation. Next thing on our steps is our implicit. So what we're going to do is we're going to take this equation and we're going to differentiate it implicitly with respect to what? Look at our derivatives over here. These are both with respect to what? T, time, right? So we want to differentiate this equation with respect to time so that we'll get dH dt and dB dt to come out. So here we go. Take the derivative with respect to t on the left, and then take the derivative with respect to t on the right. Let's take the easier part, the right side. What's the derivative of a constant, regardless of what it's respect to? 0 always, right? So the right side's 0. All right, on the left side, I have an addition between these two, right? So I can differentiate each one individually. What is the derivative of h squared? Be careful, chain rule, right? So derivative of h squared would be first power rule, so 2h, but I'm not done, right? Now times the derivative of the base, the derivative of h, with respect to t, which would be, I have to sneeze, dH dt. Okay, I think it's gone. Right? Any questions here? Power rule first, then the derivative of what's in here with respect to time, which is dH dt. How about the derivative of b squared? Same thing, right? We're going to get 2b, chain rule, 2b times, and then we have the dB dt. And that's it. I mean, we're done with the implicit differentiation. We take a look at this now, and we just kind of glance, go through it and say, what do we have? Is there anything we don't know right now? Because I'm ready to try and solve the problem. I can now, after the differentiation, I can actually fix everything in time. I can say, okay, now I can look at this situation. So do we know what h is at this particular instant in time? Do we know what h is? Yes, it's 3, right? Do we know what dH dt is? Yes. Do we know what b is at this moment in time? Not directly, right? But isn't b just this side right here? Right? And if we're looking at this picture here now, can't I solve for b using Pythagorean? Yes. So even though I don't have b, right? I don't have b directly, I can do some work to get b now. And then dB dt, do I have that? No, but that's actually what I wanted to solve for, so I'm happy to see it. So there's only really one thing I need to do before I proceed and get an answer, and that's figure out what b is. All right? So let's find b by coming back over here, and let's just do this work. This is b squared plus 3 squared equals 20 squared. I'm just using Pythagorean, right? I'm using the same formula we had up here. You could have just used this if you wanted to, but I'm going to the picture because I think it makes a little more sense in the picture. So this is b squared equals, that's 400, that's 9. You're going to subtract it. So what is that, 391? Then take the square root. And we will only take the positive root because it wouldn't make sense for b to be negative here. Square root of 391. I'm not even going to get that as a decimal. I'm just going to leave it like that for now. And I'm on my final step now. I'm going to actually go get dB dt. I'm just going to plug everything into this equation we had right here. Plug everything we had right here. Let me do it right here for you. All right, so this continued up here. We have 2. H we said was 3, right? times dH dt, which was negative 0.5. Right? So 2 times h times dH dt, which we said was this. And then plus 2 times b. Well, we just said b was the square root of 391. And then we have dB dt, which is what I'm trying to solve for, then equals 0. So if we do this, 2 times 3 is 6, right? And this is a half, right? Negative a half. So negative 1/2 times 6 is negative 3. So this is negative 3 right here. And then plus 2 square root of 391 times dB dt equals 0. And I'm trying to solve for dB dt. That's what I'm trying to get by itself, right? So I'm going to first add 3 to both sides of the equation. Add 3. And then I'll divide by 2 square roots of 391. And that will, so take this side, divide by 2 root 391, divide this by 2 root 391, and you get dB dt equals this right here. Let me see if I brought my calculator. Let's get that as a decimal, if I have it. Oh, I do. Maybe I don't. Yeah, okay. So I'm taking 3 divided by, make sure, get my parentheses there, 391. Are there any questions while I'm doing this? 0.075, roughly. So 0.075 approximately is what I'm getting. One last thing. I have to put the units of this. So the way that I look at units is I go back to this fraction, dB dt. B is the length of that bottom piece, right? And we're dividing that length by time. So how long is B? Well, how are lengths measured in this problem? Feet, right? And then time was measured in seconds. So my answer should be in feet per second. Feet per second. There we go. So if you have a ladder, 20-foot ladder, sliding down a wall, where the tip of the ladder is moving at 0.5 feet per second down the wall, then at the moment the tip of the ladder is 3 feet off the ground, the base of the ladder will be moving away from the wall at exactly 0.07, well, approximately, because I rounded, 0.075 feet per second. Now, an instant later, that speed's different, right? An instant later. So these problems are only good for telling us what happens at instants in time, right? Instants in time. Which you might sit there and go, well, why would you ever need to know that, right? But if you think, one good example is if y'all know how a piston engine works. You know how a piston engine works? Basically, I'm not going to get into details of it, but I'm just trying to think of one specific example. When engineers are designing engines or cars in general, anytime you have moving parts, you always want to know if one part moves at a certain speed, how does that impact the speed of another part moving? So when you have a piston engine, you have a piston, it's connected to what's called a connecting rod, and you basically mix oxygen and gas together inside of a cylinder. There's a spark, there's an explosion, it forces the piston down. This piston is attached to a circular crank, and it makes this thing spin, right? So this goes down and this has to go around the circle. So you convert linear motion, up and down motion, into circular motion, and then that, of course, is transferred into your transmission and then to your wheels, and then you drive down the road. So if I know how fast this piston is moving down at a specific instant in time, I could ask the question, how fast is this point on that wheel spinning at that instant in time? And so engineers always want to know, like, at every point in time when this piston, is here or here or here, at every point in time, you want to know how that relates to the speed of the wheel or the crank. All right. I mean, that's just one example. Like, instantaneous rates of change are something that engineers look at all the time. Also, like, if you think of, we haven't had a flood here in a while, but if you've ever, I don't know if y'all remember years ago when, like, what dam was it that was almost overfilling here? Was it Canyon Lake that almost overfilled? No? I think it was Canyon Lake. But anyways, we can figure out if water is coming into some container at a certain rate, we can figure out how fast the level is rising. And we can say, okay, when it reaches the top, how fast is it coming up? We're going to do a problem like that in just a minute. But I know as a Cal 1 student sitting here, it's hard to understand how you could ever want to know about what's happening at an instant when an instant later it's different. So I know it's like, well, what's the point? Well, because we want to be able to analyze it at every extreme of the motion and everything in between. So, all right, we're going to move on. That is the type of problem that I would give on a test. It's very straightforward. This Pythagorean, there's nothing crazy. There's no, the formula's not nuts. Everything's straightforward. Let's get to something that's a little crazier. I didn't want to start with this because it was our first day back since spring break. So we had this problem before spring break where we had a plane flying overhead, right? I'm going to let you read that problem. We did this problem in class. Plane was flying horizontally at an altitude of 2 miles. The plane was flying at 600 miles per hour. And then I said, okay, at exactly the moment the plane is 6 miles from this radar station on the ground, how fast is the distance between them changing? Do y'all remember this problem enough for me to continue? Yes? Plane flying overhead, radar station. We're interested in the distance. And at a specific moment in time, right, at a specific moment in time, right there, we wanted to know how fast this distance was changing. I'm going to give you that same problem with a slightly different question. A plane is flying horizontally 2 miles high, same plane, 600 miles per hour, same situation, radar station on the ground. At the moment the plane is 6 miles from the radar station, that's exactly the same question, right, so far. How fast is the what? Angle of the tracking radar changing. So instead of trying to figure out how fast the distance between them is changing, we're looking at it more like if you're watching this plane come towards you, and just think of my head as being the radar station. If I'm looking at the plane when it's real far away, my head's watching as it comes closer, I'm going to have to move my head to look at it, right? And then it goes over, right? And I have to track it like that. Is my head rotating at a constant rate or not? What do y'all think? Think about a car. Like if you're standing there on the side of the road watching a car go by, right? You see it coming, and when it gets close to you, it's like, like that. You like the sound effect, right? Like here in this range right here, you have to speed up to keep up with it, right? And then as it gets further away, you don't have to turn your head as fast, right? Same thing happening here. Radar station's tracking this plane. I'm going to show you the animation. The radar station's tracking the plane. Look at this angle. Real fast. See how it swung through that angle? And then it's real slow. Slow, 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 fast, 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 slow, 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 right? So we want to know at a specific instant how fast that's rotating. That's an extremely important calculation if you're trying to shoot that plane down, isn't it? Right? Because if you are controlling a gun, right, a lot of our Our Navy ships have this thing on. Have you all ever seen that? I forget what it's called. Have you ever seen that like Gatling gun thing that's on our ships that tracks and shoots down missiles and planes and stuff? It's just sitting there. I forget what it's called. Maybe I'll show a video of it. But it is constantly calculating, something moving and tracking it, and how fast does it need to rotate to be able to keep up with it, right? So this is a very basic problem. We're not shooting any planes down. We're just trying to figure out how fast we're turning at an instant, right? All right, let's do the problem. Let's draw a picture, general picture. All right, so I've got the plane up here. I've got my radar station on the ground here. I know that there's a kind of an imaginary line connecting the two. That's the distance between them. And what I'm interested in mostly is the angle here, right? This angle, that angle. So I'm going to label that angle, I'm going to call it theta, because in pre-cal, whenever we had an angle and it didn't have a value, we usually just gave it a variable name of theta. I would not use x or something for an angle. Is there anything else on this picture I can draw that would be maybe useful to me?
The line of the plane is flying horizontally.
This right here, like it goes horizontally, okay, that might be useful to us.
Down.
2, right? So we know for sure this the plane's flying 2 miles high, right? So we can put a 2 from here straight down. Let's do that. Let's go from here down. Do you all agree that that's 2? I'm just kind of like drawing things to kind of give myself a reference. Let me get to the instant in time picture. It's the same picture, right? Got my plane. I've got my radar station on the ground here.